Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Let me start today's show with a huge thanks to everyone who's taken the time out to vote for us in the People's Choice Podcast Awards. Voting ends tomorrow, July 31st, and we are extremely appreciative of everyone who's voted, commented, shared, or otherwise. We'll be sure to share the results of the voting as soon as they become available. If you haven't already cast your vote, please visit twimlai.com/nominate to do so. In this episode, I'm joined by Laura Leal-Taixé, 2017 recipient of the prestigious Sofja Kovalevskaja Award and professor at the Technical University of Munich, where she leads the Dynamic Vision and Learning Group. In our conversation, Laura and I discussed several of her recent projects, including work on image-based localization techniques that fuse traditional model-based computer vision approaches with a data-driven approach based on deep learning. We also discuss her paper on one-shot video object segmentation and the broader vision for her research, which aims to create tools for allowing individuals to better navigate cities using systems constructed from visual data. And now, on to the show. All right, everyone, I am on the line with Laura Leal-Taixé. Laura is a professor at the Technical University of Munich, where she leads the Dynamic Vision and Learning Group. Laura, welcome to This Week in Machine Learning and AI.
Hello, Sam. Nice to be here.
Why don't we get started by having you tell us a little bit about your background and how you made your way into machine learning research?
Yes, so I studied actually not at all machine learning or computer vision. So I studied telecommunications engineering back in Barcelona. And then I went to do my master thesis at Northeastern University in Boston. And that's the first time that I took a course in computer vision. And so that's where, let's say, my passion for this field started. And then I decided to pursue a PhD. So I went back to Northern Germany to do a PhD in Hanover. And during the course of my PhD, machine learning and especially deep learning started to become really popular within the field of computer vision. And towards the end of my PhD is when I started to focus a little bit more or try to get into machine learning and understanding how could this be useful for the tasks that I was dealing with during my PhD. And after that, I went to ETH in Zurich for a couple of years for a postdoc. And after that, I moved to Munich also for another postdoc until recently, where I was given the wonderful chance of becoming a tenure-track professor also here in Munich.
Great. What was the focus of your PhD research?
So I was working on multiple object tracking. I started with a project where we had to track algae. And this was for to study essentially how algae get stuck or get attached into the surfaces of ships. And so basically they ruin the surfaces. And so the whole idea, this was together with Department of Chemistry and Physics. So they were really studying the possible materials that could repel these algae. And within this project, my goal was essentially to analyze the way these algae moved. And of course, they had tons and tons of video data, and they could not just manually follow each of these algae manually. So they wanted to have an automatic tool for analyzing this large amount of data. And so this is how I started with the topic of multiple object tracking. And then I moved a bit more towards people tracking because the motion of people were more interesting. There was the whole goal of analyzing the pedestrian motion for example, for autonomous driving applications. And so this is where basically I shifted more towards crowded scenes, analyzing people interaction and using these interactions for better prediction of people motion.
And more recently, you've been working on visual localization. Can you tell us about that problem and your approach to it?
Yes, so visual localization is an entirely different problem. So here, what we're interested in is estimating the position of a camera in 3D within a given scene. And you can imagine that this given scene can be either a building for indoor localization or an entire city for outdoor localization. And this scene, this model is essentially reconstructed from images using standard computer vision techniques, such as structure from motion. And from this, you can just crawl a bunch of images from Flickr and reconstruct, for example, entire cities in 3D. And so now the idea is that you're walking around that city and you take a picture of some building and you want to know exactly where your camera was located when you took that picture. And this has applications in, for example, augmented reality or robotic navigation, where you really need a very precise localization of your camera. And so this is not a new field at all. So it has been tackled in computer vision for a really long time. But recently, people started tackling this problem, of course, with deep learning. And so we were looking into this with a master thesis here at TUM. And we actually realized that people were kind of forgetting all the classic research in these fields. So they were just blindly taking neural networks and applying it to this problem, where the input was an image and the output was directly the camera pose. So what we're working on now is to kind of fusing the classic knowledge of geometry, multiple view geometry, feature extraction, and all the knowledge that was gathered in something like 10 plus years of research in visual localization, and trying to fuse this with the data-driven or deep learning methods. And within this project in particular, what we're doing is not actually trying to extract an absolute pose of the camera, which is what methods like PoseNet are doing, but actually estimating a relative pose between a camera that you know where it is located because you used it to create your model, and this new image that you're capturing. And so this method is actually much more flexible because you can go anywhere, take a picture, and as long as you have some other pictures around you that you know were used to create your model, you can actually localize yourself, which is not true for PoseNet, where you actually need to retrain a different neural network for every specific scene where you want to localize yourself. And so we have been working towards this goal of relative pose estimation with neural networks and including some geometry, multiple view geometry information. And this is the work of one of my PhD students, who she recently started. And it's also together in collaboration with Thorsten Sadler from ETH Zurich. And the ultimate goal is, of course, to handle more and more complex scenes that could not be handled before with classic methods. And by more complex scenes, what I mean is, for example, dynamic scenes. And this is where my expertise in multiple object tracking comes in. So if you are actually observing a city, it's very easy to localize your camera if your city is empty. And so you only have the buildings and the static parts in there. But as soon as you have crowds of people and all these dynamic objects, they are not good for your localization. So they're basically noise for your localization. So we want eventually to build a pipeline that is robust enough to handle these dynamic scenes.
One of the things that you mentioned is a bit of a recurring theme here on the podcast, and that is this idea of fusing deep learning based methods, CNNs, I imagine in this case, and more traditional methods to kind of inform those CNNs. And there seems to be a tension in the research about whether an end-to-end deep learning approach is, better given sufficient data and sufficient compute, or whether we should try to incorporate the various things we've learned about these various problems we're trying to solve, or the physics of given situations. Maybe talk a little bit about the model that you're building to fuse those two types of approaches and how you've gone after that specific part of it?
So that's actually a very good question, because it's really a central point that is coming up more and more in discussions within the community. So I think there was a really big shift from these model-based methods to data-driven methods, fully data-driven. And in theory, if one has enough computational resources, enough data, this is the perfect setup, because you have a universal approximator that can just express any function that you want to find. So this in theory is perfect. The problem is that data is very costly to obtain. And so now people are talking about constraining your deep architecture with some previous knowledge, as you said, like physics, or in our case, multiple view geometry. Now, the interesting question is, where do you put this information? So do you put it in the loss function? Do you constrain your activation maps to have certain shapes? Or you can also, for example, actually make your architecture more modular, so that each of the different parts is interpretable and has, for example, physical meaning. And this is still a question that is not entirely solved, right? So this is something that people are actively researching, and we don't have the ultimate answer. So how we did it for the visual localization project is essentially we proposed to mimic the pipeline of a feature matching that is also present in classical visual localization methods, where you have two images, you want to find the relative pose between them. And essentially what you do is you compute a series of features, then you try to match these features and find a pose that explains these matches in a coherent way, so that the geometry is okay for most of the matches. And this pipeline is actually very robust. And one of the problems that it has is that this feature extraction step was completely handcrafted before. So people were using SIFT features or SURF features. And this worked really well for many scenes, but they don't work, for example, indoor.
Oh, what are SIFT and SURF features?
Oh, these are so SIFT are scale invariant features. They're essentially feature descriptors, like a bit like corner detectors, and they just they tell you where an interesting, or let's say a defining feature of your scene is, and what is its descriptor. So you attach a vector to this particular feature. So when you look at the same scene, maybe from a slightly different angle, you get for the same point a very similar descriptor. And then you can say, oh, these 2 points are actually the same 3D point. They are just seen by from two different positions. But the point is that this descriptor should be very similar for the same point in 3D.
So that these SIFT features are playing a role similar to like an edge detector in classical object detection.
Yeah, for example, yeah.
You mentioned a few different ways to incorporate this geometry into a pipeline. How does the way that you've chosen to do it map up to some of the general ways that you mentioned, incorporating into the loss function, incorporating it into the shape of activations?
So it kind of approaches two sides. So one is definitely the loss function. The loss function is acting directly on the essential matrix prediction, which is the matrix that gives you the relative pose between the cameras. And the other thing is the actual architecture. So we're making the architecture modular in the sense that since we're mimicking or trying to mimic this classic feature matching pipeline, we try also to place the architecture, to design the architecture so that each of the parts mimics this visual localization pipeline. So we know that in the first CNN, you're going to extract some features that are going to be representative of your scene. Then you're going to have a matching step, and then you're going to have an essential matrix or relative pose regression. And this kind of dividing your neural network into different interpretable parts is also one way to, first of all, understand what's happening with your neural network, and second of all, include some information, some hard-coded information in the middle if you need to.
You mentioned the essential matrix. What is that, and what's the role that it plays in this pipeline?
So the essential matrix gives you essentially the relative pose between two cameras. So it tells you how can you go from a point in one camera to the exact same point, but as seen from the other camera. So it basically transforms your coordinates from one camera to the other. And this is all that we want to find. So once you have relative poses, then you can localize your camera. You can create all these maps, these 3D maps from images that I was talking about. And this is essentially what we want as a result from our algorithm.
Okay. And so how do you characterize the results of this approach relative to the alternatives, both traditional as well as entirely data-driven approaches?
Well, compared to other data-driven approaches, one big difference is that most of the approaches are still tackling the absolute pose estimation problem, which means that you have a very well-defined scene with an origin, which is the world coordinate of that origin, of that scene, and then you localize yourself within that world coordinate, which means that suddenly now if you have another scene, this other scene will have a completely different world coordinate. And so what you're going to do is you're going to have to train one neural network per each of the scenes where you want to localize yourself. And this is not something that we want to do, of course. We want to build a system that is able, with a single network, to localize yourself anywhere. And this is one of the key differences of our proposed method, which actually tackles relative pose. So you can localize yourself everywhere with a single network. This is one huge difference. And compared to classic visual localization, we also showed in an ICCV paper last year, 2017, we showed for the first time a comparison of classic methods versus deep learning methods. And we showed essentially that classic methods are much, much more accurate by even an order of magnitude sometimes in some scenes, which means that, well, deep learning is still not there yet. But an advantage that deep learning has is that it can handle, for example, large indoor scenes, which have few texture. So, for example, large textureless surfaces like white walls or repetitive structures. For example, in a building, you have all the stairs that look the same, all the doors that look the same. And sometimes, even as a person, if you go, for example, to a hospital, it's hard to know where you are in the hospital. It's very easy to get lost. And this is the same for classic methods, where they focus on these basic features and then they compare to staircases and they don't know which is which. And deep learning methods are very, very good at capturing other subtle features that help them to localize better in these repetitive indoor environments. So this is one real strength and where we see really the application for deep learning methods. And this is why also we proposed a new data set called TWiML, Large-Scale Indoor Localization Dataset. And this we also published last year in our ICCV paper. And this is a really, really challenging task to localize yourself in those indoor environments.
What's your intuition for why deep learning is so much better at that particular type of environment relative to classical approaches, and yet worse overall in the traditional types of environments?
Well, the key is that classic methods are based on these features that I was talking about before, so sift or surf. And these features are can only be present when you have, let's say, characteristic parts in your image. So if you have a white wall with no corners, no edges, then there's not going to be any feature on that white wall. While if you go, for example, to Marienplatz and you have this beautiful building, which is the city hall, it's full of tiny details, tiny corners. And so you're going to have really many features firing on that building. So when you have a localization pipeline that is based on those features, it's really easy to localize yourself in Marienplatz, for example, because you have many features to base your localization on. But if you just see a white wall and you have no features, then you have nothing to compute your camera position, because there's no features, so there's no matching happening. And this matching between 2D features and the features in your 3D model is the key to the visual localization pipeline. And so deep learning looks more at the overall picture. So looks at the white wall, but also maybe at the column on the right. Maybe there's some chair also in this scene, and tries to look at the whole picture and give you a descriptor for the whole scene. So even if you don't have many corners, or if you have like a white wall, you can also use the fact that there's a white wall without features in there to localize yourself. And this is something that classic methods don't do, or at least classic methods based on SIFT and SURF type of features.
Now, you've got in this architecture, you've got kind of this, I guess what I'm envisioning as a feature identification or extraction stage or module or something along those lines. And then, once you've done that, are you reusing existing neural network architectures to perform some of the rest of the pipeline, or is it all kind of new architectures?
No, so actually the feature extraction part is based on well-known architectures. So we tried GoogleNet, we tried ResNet. Currently, ResNet is what works best. And so this essentially, it's pre-trained on ImageNet, so it gives us a really, really good initialization for our weights. And how we use it is essentially we're training to go from the image to a descriptor, a vector of a certain number of elements. And for this, we do reuse these classic architectures. And then the rest is trained from scratch. Okay.
And how do you determine what the dimensionality of this feature vector is?
Well, this is a bit of a trial and error, right? So right now we tried using something like 2000, I think it was 2048. We also try using 4000 or even smaller. And in the end, you kind of do trial and error and see what works best for your problem.
And then taking a step back to the broader problem, you've got these kind of many images of these worlds or environments from different angles, and you've talked about the relative performance of these different types of approaches for kind of interior scenes versus exterior scenes. Are you training models that are good at one of these environments, or are you somehow integrating these and starting to look at models that can handle different scales or different transition from one type of environment to the next?
That's actually an excellent question. Ideally, so theoretically, our network can handle any type of environment, indoor and outdoor. But in practice, the best thing is to train a network for indoor and a network for outdoor. So this is, in my opinion, still okay, because you only have two types of networks. And currently, the bottleneck is actually the step before, the one where you actually train your network, which is to find pairs between your image, so the image that you are taking at test time, and the training images that you have around you. So of course you can imagine that you are in this city, and you cannot evaluate all the possible training images that you have from the city and that you use to reconstruct your model. And so you have to prune all these images. And so at test time, you arrive there, you take a picture, and you want to find, let's say, the 30 pictures that are most similar to your picture. And so for this, we use yet another CNN architecture. And it's basically solved the problem that is called image retrieval. So it retrieves images that are similar to your own image. So for example, you want to localize yourself in Munich. It doesn't make any sense to compute relative poses between your images and the images from Paris or London. So this network is able to tell you, look, these are 30 images that are most likely located in the same place where you are, roughly speaking. And then you can compute the relative pose between these 30 images and your own query or test image. And the problem is that the CNN for image retrieval that works for outdoors doesn't work so well for indoors. So now we're trying to figure out whether we need to retrain this network completely different and just use two networks, one for indoor, one for outdoor, or if we can actually reuse some of this network that actually works so well outdoors. So this is kind of what we're researching right now.
There's also a part of this that is related to scale, and maybe it's kind of the same answer, and you've addressed it. But when I think of these outdoor images, you mentioned at a square, the camera tends to be a lot further from the buildings, whereas if I'm navigating a hospital, corridor, the camera tends to be very, very close. Does just the idea of having two models address the scale issues, or do you run into scale issues, for example, depending on both within, either of these two types of environments?
So actually, we have to fix the scale of our essential matrices. So essentially what we do is we take the translation and we force it to have norm of 1. And what we're essentially saying is we're fixing the scale of our essential matrix. Then we train the network to predict only essential matrices with this particular scale. And then at a later stage, we will triangulate from all the training images and the relative poses. We will triangulate the real scale and the real pose of the image at test time. And so with this, actually, we can handle varying scales. So it's not to say that the network is very robust to all the range of scales. So this is also something that we need to dig into. But theoretically, you can actually handle any type of scales.
And how about generalization? How do you explore the generalizability of this approach?
That's an excellent question, because what we have recently observed is that one of the advantages of our method is that since we're predicting relative poses and therefore we can use any image from any scene, now we're not bounded to one scene, we can use much, much more training data. And we have observed that the more training data you use, of course, the better your localization is. So first it gets worse, but then it gets better. But still, you do need to see some examples from your test scene to be able to localize yourself properly there. So this is actually something that we're trying to figure out. Why is that? Because technically, the generalization power of the network is not perfect yet, because ideally you would want to train on a set of scenes and then have a completely new scene that the network has never seen before and be able to localize yourself there also. Mm-hmm. Well, this is not entirely true yet. So it does do a fairly good job, but it does a much, much better job when you see at least some images from that test scene. And so the generalization is still something that we're looking into.
Oh, really interesting. Really interesting. So you're also doing some work on object segmentation. Is that related to this project, or is it a totally separate effort?
Well, it's all part of the interest of my group, of the Dynamic Vision and Learning group, which is to actually be able to analyze the dynamic scenes around you. And this, of course, englobes a bunch of problems. So ranging from the multiple object tracking problem, where I started my PhD, to the visual localization, which, of course, we're working also on video localization, and to be able to fully analyze what's happening around you and also analyze it in time. So not only image-based, but video-based. You also need to perform, for example, video object segmentation. And this is one project that we are also doing in collaboration with people from ETH Zurich. And in this particular project, what we wanted to do was we wanted to tackle the problem of supervised video object segmentation. And by supervised, what I mean is that you're given in the first frame of your video a perfect mask that expresses which object you want to follow, which object you want to segment in your video. And so your goal now is to segment this object to find out which pixels in the following frames belong to this particular object. And so you can imagine that this is kind of easy if the object doesn't move much, if the object doesn't change the appearance much. But as soon as the object, for example, turns around and now you're seeing a completely different side of the object, or the illumination changes, or the position of the camera changes, these are all big challenges for this problem. And so what we proposed in a work that we presented at CVPR 2017 already is to actually do this fully data-driven. So there is this wonderful data set created by Disney Research and ETH people that is called the Davis dataset. And this contains really, really accurate segmentation masks. And by accurate, I mean sometimes crazy accurate, where you see, I don't know, the hair of horses segmented out one by one. So it's really crazy. And so with this, now you have like this wonderful source to train your networks. And so what we propose to do is to actually, so the key idea in that paper was actually the training scheme. So it's not a classical training where you just input your data and you get your output. But first you take this network, which is a classic convolutional neural network. You kind of pre-train it for the task of video object segmentation. So you give it a bunch of masks of objects and you train your network. But what is happening now is that your network is trained to do some sort of foreground-background separation, but it doesn't know which object you actually want to follow, right? You just have trained it with a bunch of objects. You can segment a bus, a car, a chair. So there's all these types of objects in your data set. And so now you still have to tell your network which object you actually want to segment. And so how we do it is in a second training stage. We use this first mask of the object that we do have available, and we kind of overfit the network to that mask. So we say, really learn the appearance of that particular object. So overfit your network to that particular object. And then the only thing that you need to do is you run your network for the rest of the frames, and it will be able to segment your object for the rest of the video. And this was actually a really, really novel way of doing video object segmentation, and there has been a bunch of works that have followed later this paradigm. And this was what we presented at CVPR 17, and it's called Osmos, for one-shot video object segmentation. And the idea is that, so why we call it one-shot is because you only see the object once in this first frame, and then you're able to segment it and tracking over the whole video.
I'm trying to wrap my head around how you would go about the overfitting part of the training. And maybe the question that I'm coming to is this process something that is automatable or something that you can build into an automated process, or is it a very manual process that needs to be, supervised by a researcher or a practitioner in order to work?
No, essentially, this is completely automatic. So the only thing that you need is the mask of your object for one of the frames. And then you pass this mask as a training example to your network. You do all sorts of data augmentation, for example, and you train your network for really quite some iterations. And during this process, essentially what your network learns is what is the appearance of this object and what is the appearance of the background. And this is completely automatic. So as long as you have the mask of your object, you're good to go. Of course, the bad thing or the small drawback is that if your background or your object change the appearance too much, for example, a new object appears on the scene, or a second object that looks exactly like your first object appears on the scene, then this is going to be a problem. So we had this sequence, the famous two camel sequence, where you're segmenting this camel that is moving along, and then a second camel appears on the scene. And of course, the second camel looks exactly the same as the first camel. And so our network suddenly says, well, this is also my object. I also want to follow this. And so it segments the two camels. But now the problem is that you only want to segment one camel. So what you can do is provide another training image to your network where you have the two camels, And one is segmented as your true camel that you want to follow, and the other is segmented as background. So you don't really care about the other camel. So now you're giving your network the further information that there's a second camel in the scene, but you don't really want to segment it. And with this, you can actually correct your network and fine-tune it a little bit more towards only the first camel. And so now you will be able to segment only one camel in this scene.
Does this apply to specific types of objects? How broadly does it apply? For example, what is the types of objects that are in this Davis data set? And does that, to what extent does that constrain the model, or is the model focused on those types of images?
So actually, you can tackle any type of object. This is completely independent from the object types. Davis has quite a wide range of objects, I would say. But the interesting thing is that we're not basing ourselves on object proposals or on object classifiers, but it's really this foreground-background separation. So if you have a picture with whatever strange object, and this object is segmented out, the network is going to be able to learn the appearance of this object. And it doesn't matter if it's an elephant or if it's a chair, you're going to be able to follow it. Now, of course, if you are constrained by certain object types, you can do a better work. And indeed, we also worked on that in the upcoming journal extension for this paper, which we also published last year. And this was the idea that you can use all these object proposals, for example, coming from Mask RCNN, to kind of help you and guide you through the segmentation. So if in the first mask you find that you have a lot of overlap between your segmentation and, for example, the proposal of a motorbike, then you're kind of sure that the object that you're trying to follow is a motorbike. And then you can constrain your segmentation also with a series of proposals that Mask RCNN gives you. But this is something that is, it's kind of an extra to improve segmentation, but you don't need to do it. So if you don't know what object you want to follow, you can still use the method as it is, and it will still be able to follow it.
There was another project I came across that you were working on called Social Maps. What's that one about?
Yes, so Social Maps is actually a bit of my vision of what computer vision and AI can do for society. So in this project, I actually proposed this whole research project for an award. So it was this research grant proposal, and I was lucky enough that it was accepted for the Sofja Kovalevskaja Award by the Humboldt Foundation last year. So very few really talented researchers get this award, and I was lucky to be in this pool of researchers. And
congratulations!
Thank you very much. Well, the main advantage, of course, is that it comes with quite some money, 1.65 million euros. And with that, of course, I can pay for PhD students, for equipment. So this is really the big advantage of such an award, that I was able to start my research group right away. And so I have right now 3 wonderful PhD students that are working really hard. And so all these projects that I mentioned are actually with all of them. And essentially the project Social Maps is very much related to the idea that I've said before, that we want to understand these dynamic scenes around us, but it has a very specific application. So if you think about Google Maps, for example, you see that they are really an excellent source of static information. So they have very precise maps of where roads are, where shops and restaurants are. So wherever you want to go, Google Maps is going to give you a really optimized route that you can follow, and you will get to your place wherever you are. And so the idea, though, is that this is still a relatively limited information, because it's only static information. And what I would like to input into maps is the social information. And so what I mean by social information is essentially how pedestrians, how people use public spaces. So I want to automatically analyze the motion of pedestrians, what is happening in the streets in real time. And I want to input this information into maps. So, for example, let's assume that I have to go from my home, which is in the south of Munich, and I have to go to my workplace, which is actually in Garching, so quite far away. And I'm taking my car and I'm putting into Google Maps my destination, and then Google Maps just tells me a way to follow. But let's imagine that now I have some cameras in the middle of the city of Munich, and I can detect automatically that there's some demonstration starting. So there's a bunch of people gathering, they're cutting the streets, so I'm not going to be able to pass through those streets. Now, if you take Google Maps as it is now, you will only be notified about this once there's already a traffic jam. So traffic reports are included into Google Maps, but you don't want to be the first one that is stuck into traffic. So I want to be able to detect how people use public spaces and whether there's a demonstration or whether kids are coming out of school. I want to be able to detect it fast by using this dynamic scene understanding and using computer vision and AI. And I want to input this information into maps so that now I don't get the normal optimized route, but somehow a social route. And by social route, what I mean is I want to decouple pedestrian traffic from vehicle traffic. So if cars are going always in certain roads, and now these roads are being used by pedestrians, I want to tell cars to use other routes or other roads. And this is kind of for example, one of the short-term applications. But of course, in the long term, having access to all this data and all this analyzed data, so trajectories of pedestrians, how pedestrians use public spaces, where do they tend to cross, which exits, for example, from a railway station do they use most? If you provide this information to people that are actually planning the cities, so the urban planners, then they can hopefully design better cities also for pedestrians. So this is kind of the long-term goal of this project, Social Maps.
Interesting. It makes me think of a kind of a map system like Waze, but curated using or updated using video information as opposed to this telemetry from other, drivers using the app.
Exactly. And the advantage is that you don't have to share your information. So you're just there and things are just detected. But of course, you're not identified, you're not followed. So it's just about following the trends of people, not the actual persons. I think this is an important difference to make here.
So it sounds like the projects that we've talked about you kind of think of as individual pieces within this overarching vision of social maps. Are there specific projects that you are working on that get you to the map piece, or does that come later?
So that comes a bit later. So I'm more interested in the dynamic understanding part. So I have also one PhD student that just started and is going to work more on what we talked about before, some constraining networks with physical models, and in particular apply them to multiple object tracking. So this is still a problem that is not solved. So we, in 2014, opened a benchmark for multiple object tracking called Mod Challenge. And you can see there that multiple object tracking methods have been really pushing the state of the art up. And so they've become better and better. But there's still tons of problems there. And in crowded scenes where you can barely identify one pedestrian from the other, this is still a big problem. So we want to still work on that particular problem. We want to work also on semantic segmentation, so identifying where in the city you are and which part of the city you're observing. Of course, for moving cameras, this is when the visual localization project comes in. And then I have also one other PhD student working more on general training or improving the training, making it easier to train big networks. So working more on a bit theoretical machine learning. So it's all these little projects that are coming together, but I'm still not working on the part of the actual map. So I think Google Maps already has a good architecture and a good construction for these maps. So it would just be about providing this information. So performing this motion analysis for pedestrians. And that's the main work of that I want to tackle.
Well, it sounds like really exciting work. Laura, I really appreciate you taking the time to chat with me about it. Thanks so much.
Yeah, thank you very much for inviting me. It was great.
All right, everyone, that's our show for today. For more information on Laura or any of the topics covered in this episode, head over to twimlai.com/talk/168. Don't forget, July 31st is your last chance to nominate us for this year's People's Choice Podcast Awards. Head over to twimlai.com/nominate and cast your vote right now. As always, thanks so much for listening, and catch you next time.